Hello, good evening all of you. Welcome back to ACE Online. Today we are going to discuss some basics about DC machines and synchronous machine. So which is mostly half of the syllabus of electrical machines. Okay, so let's see that. Before going to this little basics, so basics in the sense I will give some information regarding constructional, what are the difference between DC machine and synchronous machine. Okay, some details we will see. And after that we go to the previous questions, whatever asked in the previous KPTCL or KPSC or JESCOM or Bangalore Water Board, any state electricity board examination, some questions we have, we will cover that. Okay. Now, before that, let's see what is the weightage of this DC machine and synchronous machine combinedly in KPTCL or any state electricity boards of Karnataka. So here, approximately we are getting 5 to 8 questions. Approximately from previous observation, previous papers observation, but in some of the years we have many questions in synchronous. In one paper I observed there are many questions from synchronous machines. Okay, like 7 questions, 8 questions directly we have from synchronous only. Okay, but it won't repeat every year. So on an average we can expect from synchronous machine 4 to 5 questions, and from DC machines we can expect 3 to 4 questions. Okay, now from the previous papers observation, so I came to know some topics we need to focus more. So these are some important topics in DC machine and synchronous machine. In DC machines, first we are getting many questions many times from EMF equation of DC machines. So observe from EMF equation, direct questions. What is EMF equation of DC machine? EMF, whether it is generator or motor, anything. In generator we call EG, generated EMF or induced EMF. In motors, the same EMF in armature we call back EMF. Okay, so equation is same. What is that? Z phi n p by 60A. In that Z constant, because conductors, that is number of conductors always constant in the generator or motor, and poles always fixed. 60 divided by 60A we have. 60 constant, A is the parallel path, that is also constant. It depends on the type of winding, lap connected or wave connected. Okay. Now, EMF is directly proportional to speed and flux relation. From this relation, many times there are questions on DC machines. Okay. So you need to concentrate this relation, EMF equation. After that, we have questions on characteristics. Characteristics of DC generators, characteristics of DC motors, both. Particularly in motors, if you talk, which characteristics is important? DC series motor characteristics important. Okay. So what is the speed versus IA characteristics? Shape. And what is the torque IA characteristic? Shape. Before saturation, after saturation. So this type of questions, and direct graph also given. So characteristics important in DC machines. Next, speed control methods and starting methods. So speed control of DC motor. How to control speed of DC motor? We have some methods, mainly 3 methods available. Flux control, armature resistance control, and voltage control method. So these 3 methods. But if you go to induction, so previously we have seen, there are many methods in induction motor. That's why if you get any question like which motor we can control the speed easily, induction motor or DC motor? The speed control of induction motor is very simple. So we have a number of ways to control. Stator side we can control, or rotor side we can control. Okay, many ways available to control the speed of induction, but not DC motors. Okay, DC motors only 3 methods available: flux, resistance control, voltage control. That's it. Okay, so that method is important. And which method will give higher speed or above rated speed, below rated speed, or constant power drive, which method is suitable? So these are all will come in the speed control methods. Next, starting methods. Starting method of DC motor. So what are the methods we use to start a DC motor? Yes, 2-point starter, 3-point starter, or 4-point starter. So you should know the clarity. 2-point we use for what type, or what are the 2 points in that, or 3-point starter we are calling. What are 3 points in that? Similarly 4 points. So, and you should know the differences and what is advantage of 4-point over 3-point. So, there is one drawback in 3-point starter. That's why we go to 4-point starter. Okay, this type of questions we have in the, so these three related to DC machines. Okay, so most of the questions in previous years I observed from these topics we are getting questions. Next, remaining from synchronous machine. First, armature winding of alternator. What is the importance of this? Yes, whatever the armature winding we are using in synchronous machines, maybe generator or motor, what is that? Distributed winding and short pitch winding. Why we distribute? Why we short pitch? To eliminate harmonics in EMF equation, we are using this distributed winding and short pitch winding. So there are some questions based on pitch factor or distribution factor, and combination of these two, the product of these two we call winding factor. So there are some questions directly on this armature winding concept. So you need to focus on this armature winding of alternator. Okay. After that, armature reaction and voltage regulation. If you ask what is the most important topic in alternators or synchronous generators, is my answer is this one, armature reaction. See, maybe it is theoretical. Armature reaction is theoretical topic. Here you don't get any numerical based on armature reaction. But armature reaction is very, very important. The reason is, if you don't know about complete armature reaction of this synchronous machine, you cannot understand further any topic in that. That is the importance of armature reaction. Like voltage regulation or voltage drops in alternator or characteristics, or after that we have parallel operation mainly. Complete parallel operation, we can answer the questions if you know the clarity of this armature reaction. That much important it is. Okay. And voltage regulation. Voltage regulation anyhow, it will come in transformers topic, it will come in DC generators and also synchronous generators. In all these we have voltage regulation. Conceptually it is same, but there are some important differences in transformer and DC generators or synchronous generator, DC generator if you compare. Okay, and the numericals on this voltage regulation little important, and we have some regulation methods like EMF method or synchronous impedance method we call. After that MMF method, ZPF method or ASA method. So you should know the clarity of these methods. After that, characteristics of this alternator. So we have OCC, SCC, zero power factor characteristics like this, and power equations. And from power equations also directly we have questions in the previous examinations. Power, output power of generator or output power of motor or input power of motor. These power equations you should be perfect. Okay. So mainly where the problem we get is, if you come to this synchronous or induction, we have three-phase power calculation and single-phase power calculation. So generally we do some mistakes while doing calculations of three-phase powers. Because substituting line voltage or line current, you will get confused here. So little you need to concentrate on this power equation. Okay. And finally we have parallel operation of alternators. So these are the most important topics in case of synchronous machines. In synchronous machine, these are the most important topics. Regularly, many times we have questions on this. Okay. So this is the weightage and important topics we need to focus on these topics, particularly before examinations. Next, let's see. In DC machine, what is the syllabus and what we will cover? Okay. So first we will start with construction in DC machine. Construction. So here construction also important for competitive examinations. Generally for gate point of view, it is not that much important construction point, but for competitive examination it is very important. Particularly in construction of DC machine, we have many parts like yoke or stator frame we call. After that field poles, then commutator, brushes, armature core, armature winding. Okay, so you should be perfect in the differences of this construction details of DC machine and synchronous machine, because you may get question in particularly interviews. What is the difference between a DC machine and synchronous machine? Then you should not say like it is giving DC, it is giving AC. It is okay, but constructionally, what is main difference? Tell me. Can we treat a DC machine as a synchronous DC generator as a synchronous generator? Yes, if commutator is removed, and in place of commutator, replace commutator with slip rings and rotate the DC generator at one synchronous speed, constant speed. Now we can treat that as a synchronous generator. Okay, next. In the construction, we have stator frame, field poles, commutator, brushes, armature core and armature winding. Particularly that last one, armature winding calculation, important in DC machine also. Okay. After that we go to types of DC machines. Types, we have mainly two types, self-excited, separately excited. Again in self-excited we will divide it is into some number of categories, that is shunt, series, compound. Again in compound we have different categories again. Okay, you should be perfect in this. And armature reaction and commutation. So anyhow, this armature reaction we will get in both DC and synchronous. Conceptually both are same, but little explanation wise it will be different in case of DC when compared to synchronous. In synchronous, the armature reaction is very easy to understand because direct phasor diagrams we draw, phasors, and from there we will consider what is the reaction happening, but not in DC machine. So we have to take complete diagram and the field directions, then only we can understand the armature reaction of DC machine. Okay. After that, characteristics, then starting and speed control of DC motors and electric braking. What is the methods of electric braking? So this will be common for every motors, not only for DC it is. We use dynamic braking, also called resistance braking. And next is plugging, also called reverse current braking. And another one is the efficient brake is regenerative braking. Okay, so this is in electric braking, it is same for all motors. After that, losses, efficiency calculation, and tests on DC machine. Tests. Generally, tests we don't have in GATE syllabus, but it will be there in every competitive examination. So mostly we are getting some questions on tests also, like field test. We conduct for which motor? Like this type of questions, field test. What is the reason or what is the purpose of conducting field test, or what is the purpose of conducting Swinburne's test or Hopkinson test? So this type of questions on the tests of DC machine. Okay, next. So this is the syllabus we have from DC machines, and from synchronous machine, let's see that. From synchronous we have first anyhow construction will come, and then EMF equation of alternator, and then armature reaction, voltage regulation. So same it will come like in DC also, armature reaction, voltage regulation, and characteristics of alternator, power flow equations, parallel operation of alternators, and finally synchronous motor. Out of these, the most important topic is this: parallel operation, armature reaction, and voltage regulation methods. Okay, so mostly there will be at least one question on the parallel operation. That much important it is. Okay, so this is the syllabus we have from synchronous machines. So this is about the syllabus for both DC and synchronous. Now let's see some differences between the DC and synchronous machine. What is the main difference in DC and synchronous? Generally, whether it is DC machine or synchronous machine, DC generator or synchronous generator, let us take. In every generator we have two windings. One is field and another one is armature. Where we place this field winding and armature winding in DC machine and synchronous machine. So first, if you talk about DC machine, where we place field winding or field system, let us take field winding, where we place field winding and where we place armature winding. Tell me, stator or rotor? We have two cores, stator and rotor. Tell me where we have field winding in case of DC machine. Try to interact, then only the session will be good. Try to interact. Where we place field winding and where we place armature winding. Tell me. . 。  . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Yes. We will place field winding on stator and armature winding on the rotor. Field winding on stator and armature winding on rotor. But in synchronous generators or synchronous machine, it is reverse. But can we place any place? Can we place it at stator or rotor? Suppose field winding in DC machine. Can we place the field winding in the rotor and can we place the armature winding on stator? No, not possible. Possible, but you don't get DC there. That's why in DC machine particularly, we should place the armature winding in the rotor and field winding in the stator. Whatever the poles we have, the projected poles. Okay. Yes. See here. In case of DC machine, field winding we place on the stator and the armature winding will be there on the rotor. Can we place reverse it is? No. Because according to Faraday's law, whatever EMF induced in any generator, that is AC only. But DC generator means what should be the output voltage? DC voltage. So when DC will come? Because of this commutator. So we have one device in DC generator or DC machine, that is commutator. So very important function it is. So this commutator will convert induced AC into DC, pulsating DC. So commutator is a device, whenever it is rotating, it will convert that AC into DC. But whenever it is not rotating, it cannot convert. So that you can understand from simple loop generator concept. Okay. So in case of DC machine, armature winding we should place on rotor. This is fixed. Otherwise, you never get DC voltage. And field winding on stator. But in case of synchronous machine, where we can place, tell me, in synchronous machine? The field winding, generally we place on rotor. Field winding generally we place on rotor and armature winding we place on stator. Armature winding we place on stator. Okay. So this is generally, but can we place reverse? Yes. So let us place the same field winding on stator and armature winding on the rotor. Yes. It is possible or not? Yes, you can generate voltage. That is also possible in case of synchronous generators. But in DC generators, it is fixed. Always field winding should be on stator and armature winding should be on rotor. But in case of synchronous machine, anywhere you can place field winding on rotor or stator, and this one can be placed on stator or rotor. But out of this, preferred combination is what? Preferred combination is this one only. Field winding on rotor and armature winding on stator. Okay, it is fixed. Why? Because there are some advantages with this combination. That's why we go to this combination only, field winding on rotor always and armature winding on stator. So you will know that what are the advantages of placing field on rotor and armature winding on stator. Okay, so this is some constructional difference between placement of winding in DC machine and synchronous machine. First of all, to understand these rotating machines, an electrical student should have some formulas, some we call Fleming's left hand rule or Fleming's right hand rule or right hand thumb rule. So these rules you should be perfect. Otherwise you cannot understand this. So these rules you should be perfect. Okay. Fleming's right hand rule, Fleming's left hand rule and right hand thumb rule. Now Fleming's right hand rule we use for what purpose? Tell me. So just try to recollect once Fleming's right hand rule, left hand rule and right hand thumb rule. Tell me. Fleming's right hand rule. So Fleming's right hand rule statement is, let us place the three fingers of right hand mutual perpendicular. What are the three fingers? Forefinger, thumb finger and middle finger. Now what is the indication of forefinger in this? Flux direction. So based on this I will show you one question also, which is previous gate question and also previous many competitive exam questions also the same it is. Forefinger indicates direction of flux. Thumb indicates motion of conductor, because generator means we need to rotate the conductor in some direction, maybe clockwise or anti-clockwise. Okay, so that motion, how you are rotating, in what direction you are rotating, that is given by thumb. And what is the middle finger now? Direction of EMF or current. Okay, so this is Fleming's right hand rule we use for generators in order to find out what is the direction of EMF or current in the conductors. Next, Fleming's left hand rule. Fleming's left hand rule statement also same or not? Generally most of electrical students will take definitions as it is, but they don't realize how to learn machines. Machines is very simple if you understand in a easy way everything, every concept. Right hand rule, left hand rule, both almost same. If you know about right hand, you also got left hand, because both are same statements. See, what is Fleming's left hand rule? Again, let us keep the three fingers mutual perpendicular. Forefinger, thumb finger, middle finger. Now what is the forefinger indication or index finger indication? Flux direction. And middle finger, what is the middle finger indication in right hand? Direction of current. In left hand also it is same. Direction of current, because in motors we place a current carrying conductor. Motors. Because of that current carrying conductor, some force will develop. That is Lorentz force principle only. Now because of the force, now the conductor starts moving in some direction. So Fleming's left hand rule is forefinger is direction of flux, middle finger is direction of current. What is the direction of current flowing in the conductor? Then thumb finger indicates direction of force or torque. Based on that only we can say in what direction motor will rotate, maybe clockwise or anti-clockwise direction. Okay, these two. And one more is right hand thumb rule. So this is everyone knows almost, right hand thumb rule. What is the right hand thumb rule? If the forefinger indicates direction of current, thumb indicates direction of flux. And vice versa it is. When forefinger is current, thumb is flux. Or when thumb is current, four fingers will be flux. So around a current carrying conductor there is a flux, and the direction of flux is given by right hand thumb rule. So these three rules you should be perfect first to understand rotating machines particularly. For transformers mostly we use right hand thumb rule, that's it. Fleming's left hand, right hand, that much it is not we use. But in rotating machines everything is from Fleming's right hand and Fleming's left hand. So these two should be perfect. Okay. Now let's see some questions related to DC machine and also synchronous machine. From there we will cover whatever the topic or concept required. Okay. Let's see some questions on this. See the question. Here I have two questions, first one and second. So try to answer this first question in this. Yes, if you remove the commutator in DC machine, in place of that commutator you have to place slip ring. Okay, I hope you have the idea of slip ring. So if you place the slip ring, the same DC generator will work as AC generator now. Commutator converting AC into DC. If you remove that commutator and placing slip ring means you will get AC only outside. That is the AC generator. Okay. See the first question. In a DC shunt generator, the voltage under no load condition is dash. Try to answer this first question. Yes. Try to send, try to interact, and try to ask whatever the doubts you have. From the given options, which option is right? In DC shunt generator, the voltage under no load condition is dash. How much voltage will induce under no load condition of shunt generator? Tell me. So those whoever is having idea of these self-excited generators, shunt series compound, these are self-excited generators. In these self-excited generators, we should have some conditions to induce EMF. Otherwise, voltage will not induce. like residual flux, and field winding should be properly connected with armature. Okay, and the resistance of field winding should be less than critical field resistance, and speed of generator should be greater than critical speed. Okay, so these conditions are important. Mahesh Kumar, non-Karnataka students can apply. So I don't have complete idea of this. Just refer notification once. I think you can get the information easily. Okay. See, for shunt generator, and second question is same. In DC series generator, the voltage under no load condition. Same question for series generator. Voltage under no load condition. Yes, observe here. For shunt generator, the voltage induced under no load is rated voltage. Even the generator is no load condition, voltage will build up in that. Why? If you see the figure of shunt generator, see here. Consider it is a shunt generator. It is under no load condition or open circuit condition also we call. This is no load or open. We are not connecting any load here, and it is rotating. It is rotating, everything is there, speed is there, rotating normally. Now, how much EMF? If you place a voltmeter across this generator, how much this voltmeter will show you? Definitely this voltmeter will show you rated voltage, because even it is open, due to residual flux inside, a small flux will be there always in self-excited generators like shunt series and all. Always a small flux will be there. Once you start rotating, that winding will cut this small amount of flux. Initially, a small voltage will induce. That is called residual voltage, small voltage in the range 2 volts, 5 volts, 6 volts, 10 volts. Small voltage based on the magnitude of residual flux. Okay. So due to that, a small voltage induced, and whenever there is a small voltage here, let EG1, small voltage, 5 volts, due to that a path is there for field current or not? Yes. A small current will flow here. So there is a voltage, there is a current, because closed path available. So when there is a field current, again now flux will produce or not? Yes. So due to this field current, additional flux will produce in the winding, and that is added with residual flux. Now what is overall flux? Again increase. So whenever flux is increasing, keep on increasing, the voltage in generator also increase. Up to what it will increase? Up to the saturation of poles. So whatever the flux is produced by the poles, they will saturate after a particular field current. Saturation means every iron material will have some limit. Up to that only it can able to generate flux, or it can accept the flux through the material. Suppose you take a small iron piece. So written on that, it can hold 100 flux lines. It is the capacity of that iron material is 100 flux lines, for example. But you have 200 flux lines, and 200 flux lines you allow to pass through the small iron piece. Then in the iron piece, 200 flux lines are flowing, or only 100 is there? Yes. Even you are allowing 200 flux lines, 100 only present in that, and remaining 100 lines are leakage or waste. They are not entering because material capacity is up to 100 only, maximum capacity. This, it is saturated. It cannot accept more than that. Like that, as flux is increasing, voltage also increase up to some particular magnitude, and then constant. Because flux become constant, it cannot increase further. That's why voltage also constant. Whatever the voltage is constant finally, that is we treat our rated voltage. Therefore, in a shunt generator under no load condition, we will get rated voltages. So from the given options, 220. Rated means it may be 220 or 230, okay, but not these remaining options. Okay, this is 7 volts. Okay, next, series generator. Let us observe in series generator same condition. If it is a series generator under no load condition, take the figure for example, this is a series generator. Same thing, residual flux, everything is available, so we started rotating and it is open. No load means open it is. Now tell, if you start rotating, residual flux is there inside, small amount. So how much voltage will induce initially? A small voltage will induce. Due to that small voltage Eg1, is there any path to flow the current here? No path. There is no path for field current in this, or current through the field winding, because it is series. Field winding in series na here. As it is open, current cannot flow in open circuit. Now current is not flowing. So further flux will not increase, further voltage will not increase. So what is the answer for series generator? Tell me. What is the answer for series generator? Okay. Yes. What is the answer? Series generator. So small voltage will induce or not? Yes, induce. Due to residual flux it is. And that voltage will be there. Further it is not increasing. So from the given options, 6 volts is the answer. Why 6 volts? A small voltage. That may be 4 volts or 5 volts or 6 volts or 10 volts. But from given option, what is the small voltage? We have 6. So remaining not possible. That's why answer is 6. Okay. Small voltage will be there. Yes. Yes. Sarma, you try to contact if any your friends, if notification in Kannada. Okay, right. Okay. Next question. Let's see. Next question. Now try to answer this. So these type of questions are very important for competitive examinations. So here nothing will be there, but conceptually these questions will be present. So here this theoretical question, but it is not easy to answer this type of questions. Try to answer this. Yes, quickly. So as much as possible you give the answers, that much quickly we can do more questions. A DC shunt generator supplying power to bus bar. If suddenly the prime mover is failed, then the machine behaves as dash. So there is a DC shunt generator supplying power to the bus bar or grid. Suddenly some problem occurred in the shunt generator or prime mover failed, or mechanical input that is failed. If there is no mechanical input, is it generator? No. If mechanical input fails to any generator, it cannot behave as generator. If it is connected to bus bar, then from the bus bar it is now able to take power or not? Yes. Now power will reverse. Means it is like a motor now. Motor. So definitely it will works as motor, but what is the direction of that motor? So it will rotate in the same direction of generator, or it will rotate in opposite direction of generator. Suppose assume generator rotating clockwise. Now it is working as motor because prime mover failed. So in what direction it will rotate now? Tell me. In what direction it will rotate? Same direction or opposite direction? See, to answer this question, you should know 2 points. 2 points you should keep in mind. That is, what is the torque? First of all, tell me the torque is present in generator or motor or both? Torque, electromagnetic torque present in generator, motor or both? Yes, it is present in both generators and motors. Okay, generally we discussed about torque in motors, but in generators also there will be a torque, electromagnetic torque. Now, what is the direction of this torque in generator and what is the direction of the torque in motors? So motors anyhow, whatever the direction of torque is there, in the same direction motors will rotate. But generators torque, whatever the torque is produced, no, that is in opposite direction of rotation. Suppose generator I am rotating prime mover in clockwise. This is called prime mover torque. But internally in generator one torque will produce, that is electromagnetic torque, and that torque direction is opposite to our prime mover torque. Suppose generator rotating clockwise. Now internal torque produced will be in anti-clockwise direction, always opposite. But in motor it is same. Whatever the direction of motor is there, in same direction torque will be there. So these 2 points you should remember. And one equation here in DC motors we have torque proportional to product of flux and current. So this equation you should know. Okay, then you can answer this question. So let us consider first a DC shunt generator. Considering a DC shunt generator, let us consider it is rotating clockwise. So I am rotating. So we need to rotate. No, generator means mechanical input is our direction. We are rotating. Let us consider in clockwise it is rotating at some speed n. Clockwise it is rotating with a prime mover. Now generator supplying power to bus bar. Let us consider this is the bus bar, plus minus. It is supplying. So this is the direction of current. Generator supplies. Current is IA, IL, field current ISH. Okay, clear? Now in a generator, what is the direction of torque? Opposite direction. If I rotate in clockwise, in generator torque will be anti-clockwise. This is our electromagnetic torque. Okay, so even the torque is in reverse direction, it won't rotate reverse because our prime mover torque is greater in case of generator here. That's why it will rotate in same clockwise only, whatever the prime mover direction is there. Okay, clear up to this? This is generator. Now, if suddenly prime mover failed or mechanical input failed, so let us remove this prime mover here. Assume that prime mover is failed. Remove this. Prime mover is removed or failed. Now it cannot work as generator. It cannot able to supply because no input for this. Now what it will do? So as prime mover failed and it is connected to bus bar, now from bus bar it can able to take the current. Current direction reverse. IL reverse. IA also reverse. But what about ISH? ISH same because field winding will take the current. Same direction current will flow. Field current no change. So previously in generator there is a electromagnetic torque which is proportional to product of flux and armature current. Whether generator or motor, same relation. Okay, this is generator. What is the torque in generator produced? Anti-clockwise. Now, in case of motor, whenever prime mover failed, the same electromagnetic torque proportional to that. What is the field current? Remains same or not? Yes. No change in that. That's why flux will not reverse. It is remain same. But what is IA now? Previously IA it is supplying, but now it is taking IA reverse. That's why this IA I am taking as minus IA. Then what is overall value? It is negative. If it is positive, the torque now negative means torque direction will reverse here. So whatever the torque is there in generator previously anti-clockwise internal torque, now this torque direction will reverse. This is the torque in motor now. Now tell me in what direction motor rotates? In the direction of torque. What is the direction of torque? Clockwise. That's why motor also rotates in same clockwise direction. So previously how generator is rotating? Clockwise only. Therefore, it is working as motor and rotates in same direction as that of generator. Okay, so clear all of you this question? Is it clear? So take care of this type of questions. Questions looks very easy, it is theoretical question, but you should know about all these points to answer this. Okay, next question. Let's see next question. Now see this question. This question is completely depends on Fleming's right hand rule. Okay, direct question from Fleming's right hand rule it is. So try to apply the Fleming's right hand rule in this question and try to answer this question. First read this question, all of you. Read the question. Two magnetic poles revolve around a stationary armature. Armature stationary here. Okay, armature is nothing but conductors. Conductors in generators we call armature here. Okay, stationary armature carrying two coils, C1, C1 dash. C1, C1 dash is one coil. One coil means let us take a copper wire and wound like this. And this is called one coil. A coil may have any number of turns. And each coil is having always two sides. two sides will be there for one coil. This is one side, this is another side. C1, C1 dash, C2, C2 dash. So they are placed in the slots. Two coils, C1, C1 dash, C2, C2 dash, as shown in figure. Consider the instant when the poles are in a position as shown. So poles position is given. Okay. Identify the correct statement regarding the polarity of induced EMF at this instant in coils C1 and C2. C1 is this and C2 is this. So poles are rotating in this direction here. Clockwise. Poles are rotating. See the question. Two magnetic poles revolve around a stationary armature which is having two coils. Okay. Poles are rotating, but it is stationary here. This is armature or rotor. This is stationary. Actually, this is rotating, but in this question given reverse. Poles are rotating and it is stationary. Now also there is EMF in the coils or conductors. So you have to find what is the direction of EMF in C1 and C2 at this position of poles. Try to answer this. Try to answer. Out of the given options, which is right? Quickly. Yes, right. So direction of EMF or current generally we mark with dot or cross. Dot indicates coming outside the board, cross indicates going inside the board. So here you have to apply Fleming's right hand rule. Okay, try to apply this. See, actual Fleming's right hand rule is directly valid for rotating conductors or stationary conductors. Fleming's right hand rule is applicable for rotating conductors. Because what is the statement of Fleming's right hand? If the index finger or forefinger indicates flux, thumb indicates motion of conductor, motion, in what direction it is moving, and middle finger is direction of EMF or current. But in this question, the coils or armature is stationary, it is not moving. And who is moving here? Field or poles are moving. But anyhow EMF will come, because according to Faraday's law we should have relative variation between flux and conductor, that's it. EMF will induce in every conductor. But according to Fleming's right hand rule you can apply directly whenever conductors are rotating. But in this question conductors are not rotating, conductors are stationary, field is rotating. So here for this type of questions you should make one assumption, that is whenever field is moving and conductors are stationary, then let us consider the motion of conductor always opposite direction of field. Suppose field rotating what here? Clockwise. Field or poles are rotating clockwise. So you consider the conductors or armature winding is rotating in anti-clockwise direction. So we have to take always opposite to field direction. Okay. Now I consider the motion of conductor opposite to field. Therefore, this is anti-clockwise. Now I am assuming poles are stationary and rotor is rotating in anti-clockwise direction, opposite to field. Now you can apply Fleming's right hand rule. Apply here. This is north pole, okay, and here south pole. What is the field direction? North to south. This is the field direction. North pole to south pole. Externally, internally south to north it is. External only, no. This is north and south means flux lines will go from north to south. So this is our field direction. So forefinger is what? Forefinger indicates flux direction. Now thumb indicates motion of conductor. So when you rotate rotor or this armature anti-clockwise, tell me what is the motion of C1? In what direction C1 will move? If you rotate anti-clockwise, this is the motion of C1. And what is the motion of this C2 dash? In this direction it will move. C1 dash will move downward direction. C2 will move in this direction. So when you rotate it anti-clockwise, motion of conductors is like this. Okay? Motion. So motion direction I taken here for every conductor or every coil side. Now forefinger is flux direction. So if you want direction of EMF for C1, apply there, your right hand. So we need C1 and C2. That's why I am taking for C1. Forefinger is flux direction and thumb finger indicate motion of conductor upward. Now what is my middle finger? coming outside the board from C1. Coming outside is nothing but dot. It is coming outside, so it is dot. Okay, coming outside the C1. Coming outside. Okay, dot it is. Clear? All of you? Forefinger flux direction. Thumb indicates motion of conductor and middle finger indicates, according to this Fleming's right hand rule, the three fingers I kept mutually perpendicular. Then middle finger is coming outside the board, means it is dot here. Now automatically if it is dot exactly in opposite conductor, you will get cross. But anyhow we don't want C1 dash, we need C1. Dot in C1. Now what is the EMF in C2? What is EMF in C2? Observe C2, C2 dash. How the motion of these two conductors? Suppose if you take C2, it is exactly opposite to this field direction. Or if you take C2 dash, this upper one, it is moving exactly parallel to this flux line. So according to Faraday's law, whenever conductor cuts the flux or flux cuts the conductor, then only there is EMF. But flux line is moving in this direction and parallel to that the conductors are moving, maybe anti-clock opposite or in same direction. So there is no flux cut by the conductor C2 and C2 dash. So no EMF will induce here. So in this position there is no EMF. No EMF induces in C2. No EMF induces in C2. Option A is correct in this. Okay. Now wherever the EMF induced 0, that axis generally we call magnetic neutral axis. Remember this point. Suppose if you take a normal big figure, suppose two poles I am taking, north, south, and this is armature or rotor having some conductors. Let us take there are some conductors. Okay, like this. Now if you place conductors exactly along this axis, generally we call D axis, direct axis or polar axis we call, and the axis perpendicular to this D axis we call Q axis it is. Okay, D axis and Q axis. Now along this Q axis, generally along the D axis EMF will be maximum, but along the Q axis EMF is 0. So this is the position. No? So in these conductors you don't get any EMF. Always EMF induced in this position is 0. And this axis we call magnetic neutral axis, MNA. Magnetically neutral point, that is. See, exactly at this position, up to these conductors, suppose this position, let it is 0, let it is 180. Okay. Exactly at 0 and 180 degree position, there is no effect of north pole and no effect of south pole. But in between 0 to 180, which pole effect is there? North pole effect. And from 180 to 360, south pole effect. So some EMF or some currents will be there at that conductors. But in these two conductors, you don't have any EMF and no current. If EMF 0, current also 0 in that. Okay, that axis we call MNA, magnetic neutral axis. Okay, clear all of you this? Yes, right. So that is the first thing. So many times I said, so for competitive examinations, because it will decide our life. So never ever remember or by heart the objective type of questions, because out of 100 questions from previous years or GATE or ESE questions, if you by heart also, it will be so much struggle to your mind, and to by heart and to remember each and every option is very, very difficult. And most of the students will do, those who cannot able to learn subject actually. Okay, don't do that thing, because in the examination, due to the time span and some pressure will be there. So definitely we cannot recollect whatever you remember the questions or objective options, whatever the questions you by heart. So these will create a problem during examination, because in the same question maybe they change some little data, but options given same with only one option change. So you cannot remember, because you will remember the option whatever is right, but the remaining 3 options you don't focus. Whatever is right they will give in the option, and in the remaining 3 options they will change the values. Okay, So learn subject, you can answer any type of question further. Next question. Next. See this question. See the question. A 4-point starter is used to start and control the speed of dash. So this is previous one of the KPTCL question only. Tell me. What is the answer for this? A 4-point starter is used to start and control the speed of dash. Yes. So you should know first about starting methods. We have 3 starters: 2-point starter, 3-point starter. We have 2-point starter, 3-point starter, and 4-point starter. Okay, 3 starters we have for DC motors to start. So in these, using these starters, we are limiting starting current, because starting current run by DC motor generally very high, because at the time of just supply given, the back EMF induced in motors is 0, because armature has to rotate, then only EMF will come in that. Otherwise, no back EMF. That's why high currents will flow in that. To limit that, we are using these starters. Okay. So 2-point starter particularly we use for series motor. This is for series motor. Okay. And remaining 3-point, 4-point we use for other motors like shunt compound motors. But in 3-point starter, we have one drawback. That's why we go to 4-point starter. What is the drawback for a 3-point starter is, this 3-point starter is not suitable for high speed application. Suppose if you want to rotate your motor at high speeds, what is the method we use to control the speed of motor at above rated or higher speed? Flux control method. So in flux control method, we get high speeds. But when we do flux control, the starter automatically comes to off position. It is not suitable for high speed control. 3-point starter not suitable for high speed control, or for flux control it is not suitable. To overcome that drawback, we go to 4-point starter. So 4-point starter main purpose is for high speed operation, or for flux control method we use 4-point starter. Now read the options. It is not suitable for series motor and DC shunt motor with armature resistance control. 4-point starter we use for shunt motor with flux control only. Okay, because flux control will give high speed, no? So this is also not correct. DC compound motor is not mentioned any method here. So you can use a 3-point starter also for DC compound. Okay, so that's why none of the other 3 is the answer. Actually it is for high speed or shunt motor with flux control. If given in the option, that is correct. Okay, next question. Next, in a DC series motor, torque developed is proportional to dash. Torque. Just now I written previously. Torque in DC motors proportional to product of flux and current. Okay. If it is a shunt motor, flux is constant, or separately excited motor, flux is constant. So whenever flux constant, torque proportional to only current. But in series motor, what is the armature current and field current? Both are same or not? Yes, previously I drawn figure. Armature current, field current, both will go in same line, same path. That's why flux proportional to IA for series motor, then IA into IA will be IA square. So torque in series motor is proportional to square of the current. That's why series motors will give a very high starting torque. When compared to other motors, series motor starting torque is very, very high. Suppose if you get any question, which motor is having high starting torque? DC series motor, induction motor. Tell me what is the answer? Which motor is having high starting torque? DC series motor or induction motor? No doubt DC series motor. And what are the applications of series motor? So mostly we use wherever we require high starting torque application, like traction, okay, like locomotives or hoists or cranes. So all these places we use series motor only. And if you know AC series motor, this is DC series motor, and we are using mostly in commercial purpose AC series motor. What is that? Can you tell what is universal motor? Universal motor. What is universal motor? Yes, a motor which works for both DC supply and AC supply. That is generally we call universal motor. Generally, whatever the tools we are using, like hand tools, particularly drilling machines. So here what we are using? AC series motors only. So these are all AC series motor. So what is the torque of that? Very, very high. So you should at least one time you should able to find out how much torque it is producing. So drilling machine easily available. So if it is available, try to take the drilling machine in your hand and slowly try to press the button. So you can feel what is the torque produced by the motor. You cannot stop that drilling machine. That much torque it will produce. Okay. So torque produced by series motors is very high. Next question. Now let's see some questions on synchronous also simultaneously. See the question. Read this question. When a synchronous motor is running at synchronous speed, the damper winding produces dash. So this is produces dash. The damper winding produces. So first of all, what is the purpose of damper winding? Purpose of damper winding. So the purpose of damper winding is to eliminate hunting in synchronous machines we use. And in synchronous motor, the same damper winding we use for starting purpose, because synchronous motors are not self-start. To make it is self-start, we use damper bars. Okay? Tell me first. Synchronous motor is running at synchronous speed. Okay? Then the damper winding produces dash. The damper winding produces dash. So from the given option, damping torque, torque aiding the developed torque, eddy current torque, no torque. What is the answer? Yes, very good. No torque. No torque will produce, because the main function of this damper winding is to eliminate hunting. So when hunting, what is meaning of hunting? It is the oscillation of rotor about its equilibrium position. Suppose simple language, synchronous motor always rotates at synchronous speed, but sudden changes in loads or input supply, the speed of motor suddenly disturb. Suppose let initially synchronous motor rotating at 1500. Now suddenly the speed of motor disturbed due to some sudden addition of load on that. Maybe it reduce or maybe it increase, depends on the load condition. Now if the speed of synchronous motor is other than synchronous speed, maybe less than synchronous speed or more than synchronous speed, so that condition we call hunting condition of motors, or alternator also same. During this hunting only the torque is developed by these damper bars. Otherwise, under steady state condition, whenever it is running at synchronous speed, it won't develop any torque. It won't develop any torque. So under this steady state or at synchronous speed, the torque developed by the damper bars is 0. Suppose n less than ns. Assume that the speed of synchronous motor becomes less than synchronous speed. So when speed will be less than synchronous speed? Suppose you added sudden load on the motor. Suddenly it cannot withstand that much load. It will take some time. So during that speed will be little less than synchronous speed. And n less than ns means which motor action it is? Induction motor action. So due to this, now in the damper winding, a torque will develop. A torque will develop. Now due to damper winding, a torque is developed. Now what is the direction of this torque? In the same direction of synchronous motor torque or opposite? It is in same direction, because it is motor action, no? N less than ns is induction motor action. So the torque produced will be in same direction. In same direction of synchronous motor torque. In same direction of synchronous motor torque. So this is additional torque developed by damper bars. Developed by damper bars, which is in same direction of synchronous motor. Okay. Suppose if speed of motor becomes greater than synchronous speed. Now also there is a torque in the synchronous motor. But what is this principle, N greater than Ns is induction generator principle. Now in a generator, just now I said previously, in a generator always torque produced is opposite direction of rotation. Now the torque developed by damper rods is in opposite direction of motor torque. Okay, so from the given options, no torque is the correct one. So here given torque aiding the developed torque. This is for N less than Ns case, then it is correct. But here it is rotating at synchronous speed only, that's why no torque will produce. Okay, next question. See the next question. See this. See this. The maximum power in cylindrical and salient pole machine is obtained respectively at load angles of dash. Maximum power. So we have for cylindrical pole alternator and salient pole alternator different power equations. Power equations. For cylindrical pole, the power equation is EV by XS sin delta. Power equation. Okay. And for salient pole, the power equation is not like this. So it is little lengthy equation. It is not the similar to this cylindrical. It is different. So it is cylindrical. Tell me where it is maximum. Whenever delta equal to 90 degrees, the power is maximum. That is EV by XS. For cylindrical pole alternator, the maximum power we get at 90 degree. But for salient pole, the maximum power is less than 90 we get. In the range 70 to 80 degrees, somewhere we get maximum power. The reason is in salient pole machine, we have additional power called reluctance power. Due to that reluctance power, the resultant load angle, wherever the maximum power we get, that will reduce. So how it is, you will see in the actual concepts. Okay. So that is for less than 90. For salient pole, less than 90, we get the maximum power. And for cylindrical pole, exactly at 90 degrees, we get maximum power. Okay. 90 and less than 90, option C is correct. Okay. Next question, let's see. Clear all of you? Next. See the question. An alternator is delivering rated current. An alternator is delivering rated current at rated voltage at 0.8 power factor lagging. At 0.8 power factor lag. If it is required to deliver rated current at rated voltage but at 0.8 leading power factor, the required excitation will be dash. What is the excitation required? See here, particularly for machines, the questions in machines, we can able to answer if you know the concept behind the question. What is the main problem of these machines questions? Understanding question itself big problem. Understanding the question is big problem here. So we can understand only if we know the concept behind that. We can understand while reading the question itself. Otherwise, if you don't know concept of that, so if you read 100 times also, we cannot understand. So here, this question you can answer simply from V curve of alternators. During parallel operation of alternators, we have V and inverted V curves, power factor and armature current and IF. So V curve we draw between IA versus IF, and inverted V curve we draw between power factor versus field current. So this question also important. V curve is the graph drawn between which two parameters? V curve is IA versus IF. Inverted V graph is power factor versus field current. Now initially where it is operating? At 0.8 lagging, it is operating at some rated current. So let us consider this is some rated current. For example, I am taking it is rated current IA. Okay, it is rated current IA. Now at this current, initially it is operating lagging. So where is lagging, where is leading here? So in the V and inverted V graph, so wherever this minimum current we have, that point is nothing but UPF condition. That is UPF, that is called normal excitation at unity power factor. Okay, this is normal excitation at unity power factor, whether it is alternator or synchronous motor, we call it is normal excitation. Now this is field current, excitation nothing but field current only. More field current means more excitation, less field current means less excitation. So here field current increase. So this is over excitation. Field current decrease towards this under excitation. Over excitation always alternators operates at lagging power factor. Under excitation always leading power factor. Okay, how it is, why it is, it will come in armature reaction topic. Otherwise simply remember here. This is for alternator. Same graph we have for synchronous motor. And what is difference for synchronous motor is simple. Convert this lag into lead and this lead into lag. Interchange power factors in the same graph, that is for synchronous motor. Okay, but it is for here synchronous or alternator given. So this is synchronous generator case. Initially it is operating at lagging 0.8. Let us consider power factor 0.8 lagging. It is here, it is operating. Okay, now at same current we need to operate at 0.8 leading power factor. Where is the leading case? This side. This is leading, no? This is UPF. This side is leading, this side is lagging. 0.8 lagging is at same power factor, same current. This is 0.8 lag. Now what is the excitation here? This is 0.8 lag over excitation. If you want to operate at 0.8 leading, you need to reduce the excitation up to this point. Now it will operate at 0.8 leading. This is 0.8, consider 0.8 power factor. This is lagging, this is leading. So you should reduce the excitation here. So let us reduce the excitation of alternator up to this point. Now it will operate at 0.8 lead. Okay. So what is the excitation required? We should reduce or less excitation required. Okay. This is directly from this graph. Next question. Let's see the next question. Try to answer this quickly. Yes, right. Stability also more. Over-excited machine always stable. That may be generator or motors. See this question. In a salient pole synchronous machine, we need to find what is the relation out of this. Salient pole synchronous machine, we have two reactants. One is direct axis reactance, another one is quadrature axis reactance. So direct axis is also called polar axis and quadrature perpendicular to that. Now along which axis more gap will come? Along Q axis. In salient pole machines, the poles are projected poles like this. Okay, and let this is north, south. This axis we call D axis and this axis we call Q axis. And the reactance along D axis we call XD, reactance along Q axis we call XQ. So which reactance is higher or both are same? So easily we can answer. Always X proportional to flux. Reactance proportional to flux only. No? More flux, more reactance, less flux, less reactance. And flux inversely proportional to reluctance. Flux equal to MMF by reluctance. So X inversely proportional to reluctance, reluctance proportional to air gap. More gap, more reluctance, less gap, less reluctance. So along D axis, what is the gap here? Less. If gap is less, what is the X value? More, means XD value is higher, but XQ value is lower. So XD greater than XQ. Simple. So what is the answer? XD greater than XQ, that is option B. XQ less than XD. Okay, clear it is? Next question. Next question. See this question. See this. The synchronous reactance of synchronous machine is dash. So we have one definition of synchronous impedance. Same for synchronous reactance also. What is that? The synchronous impedance of alternator is nothing but it is the ratio of open circuit voltage to the short circuit current for the same value of field current. Generally we draw or we will find out this ZS from OCC and SCC. We have open circuit characteristics and short circuit characteristics. After drawing the both, consider same field current and then extend the line onto both graphs. And this line will touch OCC and SCC. So from OCC take the voltage and from SCC take the magnitude of current. and take the ratio of that voltage and current, that is nothing but synchronous impedance. So that the same definition we will give for synchronous reactance also, if resistance is negligible. Okay, so which option is correct from this? Ratio between open circuit voltage and short circuit current at constant field current. Option B is correct. Okay. Next question. Yes, depends on experiment values of that voltage and current also we will get XD, XQ. Okay, but directly you can also find what is the magnitude relation. No? What is the test we conduct? Slip test to find XD, XQ. That is from measurement. There also you get same relation. XD always higher value, XQ is low. Okay, so we can say high or low, but magnitude how much means we cannot find out. No, that is from experiment only we can find. Okay, next question. See this. Try to answer this question. Try to answer this. A synchronous motor connected to infinite bus bar has a constant full load of 100% excitation at 100% excitation at UPF, unity power factor. On changing the excitation only, the armature current will have dash. So this is synchronous motor. Again draw V inverted V curves like previous, but for over excitation it is what? Leading now, under excitation lagging. That lead lag will interchange for motor. Draw the same V and inverted V curve. V and inverted V curve again. Power factor, armature current versus field current. V curve is always between IA versus IF. Inverted V curve is between power factor versus IF. What is the question? It is operating at UPF initial. Operating at UPF. On changing excitation only, what is the armature current? Armature current. Options: leading power factor with under excitation, no change of power factor. So if you observe, this is our normal excitation or UPF it is. This is UPF, normal excitation we call. At UPF, whatever the field current is there, that is called normal excitation. This is over excitation, more field current, under excitation, less field current. Over excited motor is always leading. It is reverse, opposite to alternator it is. Under excitation motor is lagging power factor. Now observe what happened. At UPF it is operating. Now we are changing excitation. If excitation changes, maybe increasing or decreasing, that is not mentioned, but from option we should answer this. Leading power factor with under excitation. Under excitation lagging, no, it is. So this is wrong. No change of power factor. Definitely power factor will change. If you change excitation, power factor is varying, no? At unity power factor, this is maximum 1. So after that it may reduce both sides. If you increase the excitation or decrease the excitation, power factor will change. So third one, lagging power factor with over excitation. Over excitation leading it is, but not lagging. Leading power factor with over excitation, this is correct. So option D is correct. Okay, directly from V and inverted V graph. If you draw that, you will get the answer. Okay, next. See the last question. See this question. Read the question and try to answer this. The direct and quadrature axis reactances of a salient pole alternator is 1.2 and 1 per unit. Assuming the armature resistance to be negligible, what will be its power angle if this alternator delivering rated kVA at unity power factor at rated voltage? Okay, this is previous gate question it is. Same question given for KPTCL also previously. Answer this one. So this is salient pole alternator. We need to find load angle in this. Load angle or power angle, delta. So here we need to use one formula. What is that? Tan psi in salient pole alternator. What is the tan psi? Tan psi equal to V sin phi plus IAXQ divided by V cos phi plus Ia Ra. So anyhow armature resistance is negligible here given 0 that is. And what is the rated voltage means? Given rated values, rated kVA at UPF at rated voltage. Rated in per unit system nothing but 1 per unit. So voltage is 1, sin phi. If power factor is 1, sin phi will be 0. And what is the rated Ia? Rated kVA means current also 1 rated. And XQ value given. XD is 1.2, XQ is 1. Now XQ is 1 divided by V. 1, power factor is 1, RA is 0. So totally psi equal to 45 degrees. Psi is nothing but internal power factor angle. From phasor diagram we get this. But we need here delta. And delta is nothing but psi minus phi. Psi is this internal power factor angle. Phi is the load power factor angle. What is the load power factor here? UPF. Cos phi equal to 1, so phi equal to 0. Then delta equal to psi itself. That is 45 degrees. Okay. Load angle is 45 degrees. So what is the answer here? Power angle 45 degrees. So this is directly from equation. You should know about this equation first. Clear? Next, one more last question. See this last one. Try to answer this. The full pitch coil. So almost I am trying to cover the all topics, whatever relations are important we have from all topics of synchronous. I covered one question from armature winding. The full pitch coil in an alternator has a span of 18 slots. For a full pitch coil, what is the coil span generally? Coil span we indicate with beta. Coil span, so we indicate with beta, that is 180 degrees for full pitch. So given full pitch coil having coil span of 18 slots, it is given in terms of slot but not angle. Generally for full pitch, coil span equal to 180 degrees. So 18 slots, nothing but 180 degrees here. Means what is one slot angle? 10 degrees. One slot angle 10. Coil span is given in terms of slots, that is 18. For full pitch coil definition itself that the coil is said to be full pitch if the coil span is 180 degrees. If it is less than 180, that coil we call short pitch coil. So here 18 slots given, that is we equated with 180 degrees because full pitch coil 180 degrees always coil span. But what is the question here? If it is desired to eliminate third harmonic voltage, what is the coil span? So this is short pitch coil. In short pitch winding, we use one letter, that is alpha, called short pitch angle. Short pitch angle or chorded angle we call. Short pitch angle. We need to short pitch the coil by some angle. How much? We have the formula for this, that is 180 by n. Formula for any harmonic to eliminate. If you want to eliminate fifth harmonic, 180 by 5. This much angle required. Or if you want to eliminate seventh harmonic, 180 by 7. But in the question, third harmonic given. That's why it is 180 by 3. How much it is? 60 degrees. So we need a short pitch angle of 60 degrees. So what is the coil span? But they are not asking here short pitch angle. They are asking coil span only, means beta. So in a short pitch winding, always alpha plus beta equal to 180. Remember, in short pitch winding, always the sum of this short pitch angle and coil span must be 180 degrees. Always it alpha plus beta must be 180 only always. Okay. If it is full pitch, what is beta? 180. Means what is alpha? 0. Means it is not short pitched. Short pitch means there is some alpha. Now how much angle we are short pitching? 60 degrees. Then what is remaining? Beta. Therefore the beta is 180 minus 60. How much it is? 120 degrees. So beta is 120 degrees. But they are asking the options in terms of slots. So 180 degrees means 18 slots. Means per slot 10 degrees. Now we got 120 degrees. Means how many slots it is? 12 slots. So the coil span required is 12 slots here. So how many slots we short pitch? 6 slots. Total 18 full pitch case. Now whenever we short pitch, How much angle we need to short pitch? That depends on the question. Third harmonic they given, so 180 by 3, 60 degrees. So we got alpha is 60, so remaining beta will be 120. 120 degrees is nothing but 12 slots. Clear? All of you? So with this I will stop some questions I covered totally from DC and synchronous machine. Okay. So all the best for the engineers of Karnataka, mostly from so much duration or so much time you are waiting for this examination. So I know from 2019 onwards. So don't waste the time, and as much as possible try to cover entire syllabus. So those who have completed previously in 2019, as much as possible try to complete your revision quickly, because don't wait for the examination date again. So whatever the date will be, so you have to prepare like this month or next month itself the exam date, whenever it is. So be prepared fully before the examination date itself. Okay. After that there will be a time, so you have to take number of revisions of the same subject, same concepts. Okay. So I'm wishing everyone all the best for your examination. Good night.